All right, welcome to the Explainer. Today, we're diving into something that's, well, it's a huge shift happening in AI, but it's happening kind of quietly. It's all about bringing two massive fields together: machine learning, the thing that's amazing at making predictions, and operations research, which is the science of making the best possible decision. We're talking about AI that doesn't just guess what's next, but actually helps us figure out the wisest move to make. But here's the puzzle, right? We've got AIs that can predict what customers are going to buy with like 99% accuracy. So why do companies still end up with warehouses stuffed with all the wrong things? We've got models that can predict traffic flows with insane precision, yet our cities are still just a total gridlock. So what gives? Why is it that our smartest, most accurate AIs can still lead to some really, really bad outcomes in the real world? Okay, so here's how we're going to tackle this. First, we'll dig into that whole prediction versus decision puzzle. Then, we'll look at how new frameworks are bringing those two worlds together. After that, we'll check out some mind-blowing real-world examples, get into the super important topic of fairness, and then, and this is the cool part, we'll wrap it up with a practical toolkit for all you entrepreneurs out there. All right, first up, the prediction versus decision puzzle. Let's really get into why being 99% right can still be 100% wrong. So the fancy term for this problem is loss mismatch. And all it really means is that the AI is being graded on the wrong test. Think about it like this. You have a weather app, and it's 99% accurate at predicting if it's going to rain. Sounds amazing, right? But what if a shipping company uses that app to plan its deliveries, and that 1% error happens to be a massive flash flood? That one single mistake is a complete disaster. See, the AI was built to be good at one thing: predicting rain. It wasn't built to understand the real goal, which was getting packages delivered safely and on time. That disconnect, that's loss mismatch. So how do we fix this? Well, it's not just a tweak. It's a totally different way of thinking about how we build AI. We've got to teach our models to think about the consequences of their actions, not just about getting the prediction right. And this slide just lays it out perfectly. The old way is what we call predict, then optimize. It's a two-step process. First, your machine learning model predicts customer demand. Then, you hand that number over to a totally separate system that decides how much inventory to order. The problem is, these two systems don't talk. The prediction model has no clue that its tiny little errors are causing huge headaches for the inventory system. But the new way? End-to-end learning. It's just one step. The AI learns to make the decision directly. It's not just trained on accuracy, it's trained on the final outcome, what really matters, the bottom line. It's learning from reality, not just from a number in a spreadsheet. This whole new approach is called integrated learning and optimization, or ILO for short. And that chef analogy? It's spot on. The old AI was like a chef who was obsessed with measuring the ingredients perfectly, just following the recipe to the letter. But the new AI, the ILO chef, this chef learns by tasting the final dish. It doesn't really matter if the pinch of salt was a little off, as long as the meal is absolutely delicious. It's all about the end result. And hey, this isn't just theory. This new way of thinking is already letting us crack problems that, honestly, we thought were impossible. Let's look at 3 pretty amazing examples. Okay, first up, complexity on a massive scale. Just imagine for a second that you're in charge of a city's entire network of electric vehicle chargers. You've got thousands of cars, right? And every time one plugs in, it pulls power, affecting every other car trying to charge. How on earth do you manage a system with a million moving parts like that? Now, the technical name for this kind of puzzle is a weakly coupled Markov decision process. Whoa, that's a mouthful, I know. But the idea behind it is actually pretty simple. You've just got a whole bunch of independent players, the EVs in this case, who are all competing for a shared resource, like the power grid. Trying to coordinate every single one of them, well, it's an absolute computational nightmare. And this table just shows you the breakthrough so clearly. The old way, the fluid model, basically just looked at the average behavior of all the cars. It's like taking a really blurry photo of a crowd. You see the crowd, but you lose all the individual details. And this meant you got a pretty big error, which actually got worse the more cars you added. But the new approach, the Gaussian approximation, this one actually models the noise in the system, all the little random things individual cars do. And the result? The error gets tiny. It actually shrinks as you add more cars. It's like going from that blurry, out-of-focus photo to a super sharp, high-resolution picture where you can see every face. Okay, let's move on to our next puzzle. What happens when the stakes are literally life and death, and you just can't trust your data 100%? Think about a self-driving car trying to see through thick fog, or a doctor looking at a really grainy x-ray, trying to make a diagnosis. How do you make the right call when you're basically flying blind? Well, this is where something called distributionally robust optimization, or DRO, comes into play. You can think of it as a kind of strategic pessimism. Instead of just planning for the most likely future, a DRO system prepares for the worst plausible future. It's constantly asking, okay, given all the uncertainty here, what's the worst case scenario? And how do I make a decision that's still safe, even if that happens? It's not about what should happen, but what could happen. And get this isn't just a cool idea on a whiteboard anymore. Thanks to some really advanced math, stuff like Bernier's theorem, which is all about figuring out the most efficient way to morph one set of data into another, we can actually apply this robust thinking to the messy, complicated data we see in the real world. What that means is we can now build AI for things like self-driving cars and medical tools that are designed from the ground up to be tough and reliable, even when things get weird. All right, for our third puzzle, let's talk about the tech that's on everyone's mind. Large language models? I mean, LLMs are amazing, right? Super creative, but let's be honest, they are notoriously bad at math and logic. They can just make stuff up. So how do you harness all that creative energy from an LLM to cook up a business plan that, actually works on paper? The answer is a framework called SOLID, and it's basically a structured conversation between two different types of AI. Think of it like this. You want to start a new coffee shop. First, you have your optimizer AI. Think of it as your super strict digital accountant. It crunches all the numbers and gives you a basic, solid plan. Then it hands that plan over to the LLM AI, your creative strategist. The LLM doesn't just look at the numbers. It reads food blogs, checks out local news, sees what's trending on social media. It might come back and say, hey, what if we added a crazy new lavender latte? Or what if we did a pop-up at the farmer's market? Then all those creative ideas get sent back to the optimizer, who reruns the numbers to make sure the cool new plan is still profitable. It's the perfect mix of creativity and cold, hard math. So we can build these amazing systems that are smarter and more robust. But that leaves one huge question. Are they fair? And this brings us to what might be the most important and most difficult puzzle of them all, the human one. There's a line from a recent research paper that just cuts right to the chase. Fairness is more than algorithms. And that really is the heart of it. You can't just code fairness into a system like a feature. Real justice is, well, it's a lot more complicated than a well-written algorithm. So researchers took a deep dive into the well-known COMPAS dataset, which is used to predict the risk of someone reoffending. And what they found was really unsettling. Even when the algorithm's risk scores were carefully tweaked to be fair across different racial groups in the short term, a really disturbing pattern started to show up over a few years. Over a 3 to 5 year period, huge gaps in outcomes appeared, especially for people the algorithm had flagged as low risk. This chart really tells the story. Right away, in the short term, everything looks pretty balanced. The algorithm seems fair, but give it time and this massive gap opens up. And the reason is actually pretty simple. The algorithm is blind. It can't see all the systemic hurdles that people face in the real world. Things like whether you can get a good job, find affordable housing, or if you have a strong support network. So even a technically fair algorithm can end up making existing inequalities even worse, just because it's operating in a world that isn't fair. So here's the bottom line, and it's so important. We cannot optimize our way out of systemic inequality. Real, meaningful fairness means that our smart systems have to be part of just and fair social policies. The algorithm is just one piece of a much, much bigger puzzle. Okay, so what does all this high-level stuff mean for you? You might be thinking this is all super abstract, but these ideas are actually an incredibly powerful new toolkit for really anyone with an idea and a laptop. So let's bring this down to earth and get practical. Seriously, think of these as your new entrepreneurial superpowers. Let's say you run an online store. Instead of just guessing how many t-shirts to order, you can build a system that learns the exact optimal stock level to maximize your profit, factoring in everything from shipping costs to warehouse space. Or maybe you're running a marketing campaign. You can use these DRO principles to set an ad budget that's resilient, one that still works even if a competitor suddenly drops their prices. You could even use these tools to do some good, like designing a microfinance model that's optimized for both profit and equitable outcomes. And of course, you can use that solid framework we talked about, pair an LLM for some wild brainstorming with an optimizer to make sure your brilliant idea is actually going to make money. Look, we're really at a turning point here. We have the tools, right now, to build AI that isn't just smart, but is actually wise. We can build systems that are more efficient, more robust, and, if we're very intentional about it, more fair. The technology is here, so the only real question left is, what problems are we going to solve with it first?